Specifically everybody. So just now we have finished resolving power for microscope and telescope. So now I'm going to do a last part of this chapter, that is what we call as polarizations. Okay, so before I actually start the polarization of a light, that is electromagnetic waves, I would like to give you a simple analogy of a string wave. So I would like to start something like this. Normally polarizations are it is a wave phenomenon. However, it is not for all the waves. When we talk about wave, we divide the wave into two parts, that is longitudinal wave and a transverse waves. And the polarization is a phenomenon which is only occurs in case of transverse waves. Alright, so let me define what is a transverse wave. This is a transverse wave. This is what we call as a traveling waves. We talk about two waves. So one wave it goes on oscillating. There is no propagation of wave taking place. And other wave propagate from one place to another. This is the example of a propagating wave. And transverse wave is defined as in a very simple mode. It is defined as the direction of oscillations is perpendicular to the direction of propagations. Then we call it as a transverse wave. So this is in oscillations. This is in propagations. This is oscillations. This is propagations. Then we call this wave as transverse waves. That is perpendicular. Transverse normally refers to a perpendicular, right? So this is what the oscillation is perpendicular to propagation. That is what we call as transverse wave. And longitudinal wave is one where the oscillation and the propagations are in the same directions. It goes like this. The example is a sound wave. Alright. So there is a rarefactions and compressions, and the rarefaction and compressions are along a direction of propagation. So therefore this is what we call as longitudinal waves. So now let me write down one simple wave equations. That is, let's say this is z, x of t is a sine k x plus omega t. This is wave equation. All right, traveling wave equations. All right. So propagation is done along x-axis. Light travel along x-axis, and this is the oscillation in a z-axis. Oscillation is in a z-axis. Oscillation in a z-axis, propagation in a x-axis. This is again, this is transverse wave. Another example I can write is in this case, the oscillation is done in a y-axis, and then propagation along a x-axis, and a is the amplitude. And then sine is a sinusoidal functions, and k is a wave number, and x is a distance travels, omega is angular frequency, and t is instantaneous time. So this is what we have. And now it is done. This is the one wavelength. This is going to be a one wavelength, and delta t within delta t, t is equal to delta t. In the time interval of delta t, this much distance has traveled. This is what it shows. All right. This is the simple nature of wave. All right. So now why we have phenomenon polarization in case of transverse wave? That's what I'm going to explain you. First, I would like to explain you this in terms of string wave. This is a string wave. So look at here. I have two mesh like this fence. I have two fence, and now this is opening of a fence. This is opening of fence. I allow a string to move like this. If I allow a string like this, so this fence will allow a string to pass through. Alright, this fence will allow this particular string, oscillation of string to pass through it. Then I put another fence whose opening is again in the same direction of previous one, and this also will allow this string to pass through it without obstacle, right? This is what we have. So the opening of these two pens are along same directions. Now my next point is, this is the same one direction. If I put this right in a horizontal part, this is the vertical, right? Now if I put this opening in a horizontal way, all right. So now these particular strings, right? The oscillation of the strings will stop at this point. Why? Because this opening is too small that it will obstruct or it will stop the oscillation of these particular strings. So the string that is out from these fans no more oscillate. Why? Because this stops oscillation of strings. So this is what we have. In case of longitudinal wave, you cannot stop. Why? Because this goes along the direction of propagation. So this is what we have in case of polarizations. So here I have given you an example of a strings. Now what exactly we are going to do here is light. And since light is electromagnetic wave, when I say light is electromagnetic wave, it is an oscillation of electric field and oscillation of magnetic fields. Oscillation of electric field and oscillation of magnetic fields. And so this is what I have. Normally we would like to show you only electric field, and this is what we call as unpolarized light. Unpolarized light. Unpolarized light. The definition of unpolarized light is the oscillation of electric field confined in this place. Alright, electric field oscillations confined in this place. So that means if this plane is XY planes, then oscillation of electric field is all along these XY planes. And another way of showing this could be this. This is, let's say this is Y, this is X. I can represent every electric field in terms of X and Y. So this is how we show. This is a simple way of showing unpolarized light. These two are not the same, right? So this is unpolarized light. This is also unpolarized light. Another way of showing unpolarized light is this. This is unpolarized light. So here the oscillation is defined in a YZ plane. This is the Y-axis and this is the Z-axis. So oscillation is confined in a YZ plane. So this is again unpolarized light. This is one. So electric field, right? Since light as an electromagnetic wave, it is all about oscillation of electric field and magnetic field. Detailed electromagnetic field, electromagnetic wave we will study in chapter number 8. Now I have here these three pictures. This is unpolarized light. You see the oscillation is random. Oscillation of electric field is random in all this area. This is what we call as unpolarized light. And this is a polarized light. So why? Because you see oscillation only in one direction, vertical. This oscillation is only vertical. Alright. Maybe oscillation is only along y-axis. And this is another polarized light. The oscillation is only along horizontal, right? So this is a polarized light. This is a polarized light. This is unpolarized light. Yes, for your kind information, whatever light we get from a source are always unpolarized light. So therefore, when we get a light from a candle, when we get a light from a sunlight, any source are what we define as unpolarized light. Now, what do you mean by polarizations? So before we start the polarizations, a phenomenon called polarizations, we would like to discuss what we call a polarized sheet. This is what we call this is what we have. So this is how we design the polarized sheets. So we will get this defined. This is molecular alignment. This is molecular alignments. Molecules are aligned. This is how molecules are aligned vertically. Molecules are aligned vertically. In this case, the molecules are aligned Molecules are aligned horizontally. Alright. And the detail of Polaroid is not this beyond our scope. So in a simple word, I say that if I align molecule align vertically, whatever electric fields oscillate vertically can be absorbed by molecules. Alright, so therefore this will stop, this Polaroid will stop electric field oscillating vertically. So what kind of electric fields comes out from this Polaroid? That is a horizontal electric field oscillation. This electric field comes out from this Polaroid. Similarly here, the molecules are aligned horizontally. Whatever electric field oscillating horizontally can be absorbed by molecules. So therefore, it will not allow a molecule. This molecule will not allow electric field which are oscillating horizontally. So therefore, what kind of electric field comes out from this Polaroid? Vertically, electric field oscillations comes out. So this is what we have. This is what we call the polarizer, whatever you say, right? So this is what we have. So this is what we call as a path axis. This is what we define as a path axis or polarization axis. Polarization axis. Same, right? This is path axis or polarization axis. So this is what we have, right? So this is what you should understand at least. Alright, so now we are done with the Polaroid. Now we are going to allow a light to pass through Polaroids. What we are going to see is unpolarized light. This is unpolarized light. This is a light source of light. Unpolarized light. Unpolarized lights. Now here, path axis is vertical. So what you see is that this is only vertically polarized light. This is a polarized light. This is a vertically polarized light. So look at here. When we define this, alright, I have something like this. This could be represented by this. Since this is the unpolarized lights, the intensity of light can be defined in a two way. That is, intensity of light can be defined by a two part. That is intensity due to these oscillations. Intensity due to these vertical oscillations, and intensity due to these oscillations. All right. So look at here. Therefore, look at here. When a light passes through this polarizer, which is vertically polarized, and if I say out of 100% of this intensity, 50 is for this and 50 is for that. Now I say when an unpolarized light is meant to pass through Polaroid, only 50% of light would pass through it. Alright, only 50%. So 50% it stops. 50% is going to stop. So therefore, intensity of a polarized light reduced to half. Intensity of a polarized light is reduced to half. Therefore, when you see through Polaroid, alright, intensity is going to reduce, no doubt. Intensity is going to reduce. Alright, so this is one very important. So now this is polarized light. This is polarized light. I have here again so once the light is completely polarized light, the oscillation is not random. So oscillation is in a particular direction. So this is unpolarized light. Now this becomes polarized light. Intensity reduced to half. Intensity reduced to half. And let's say this intensity is I naught. Let's say this intensity is I naught. And this is what we call as a polarizer. So this is what we call as a polarizer. Why? Because this particular device align electric field to oscillate in a particular directions. Or this device align oscillation of electric field to a particular direction. Alright. Now this is what we call as analyzers. So now this analyzers, alright, analyzer will defines again, you know, what kind of light it allow or to pass through it, right? So as far as this analyzer is concerned, right, this pass axis is verticals, and this pass axis is also verticals. So therefore, pass axis of two polarites are along the same directions. So therefore, you would get 100% light. So from this you get the 50, and that 50% light is what we define as I naught. When I naught pass through these polarites, since the direction of pass axis is along the direction of polarizer, so you get maximum. Alright. Now when you rotate this analyzer, then what is the effect? That's what we are going to study. And again, look at here. Again, I say this is light is 100%, this is 50%. So if I go on changing these directions, every time when I go on changing these directions, it remains 50, and what change you are going to see is the direction of oscillation is going to change. However, the intensity will remain unchanged. So a very simple word. When an unpolarized light is made to pass through polaroid or polarizers, intensity is going to remain always half. Intensity of light always reduced to half. So if I change the direction of a polarizer, if I change the direction of pass axis, still intensity reduced to half. However, what is going to change? The change is that the oscillation of electric field is going to change. There is no effect on intensity. However, what is the effect then? Alright, effect is on a direction of oscillation of electric field. That you should keep in mind. Alright, very important, right? So therefore coming to this, now here in this case, I rotate this such that these two pass axes are perpendicular. This is the horizontal, this is the verticals, this is the horizontals. Now, if this horizontal and that is vertical, that means you won't get an intensity reduced to half. This intensity is equal to I naught. This intensity is reduced to half. Why? Because this polarizer will not allow this kind of oscillation to pass through it. This polarizer will not allow this kind of oscillation to pass through it. So that one very, very important, right? So therefore, we have one very important formula or law called the last law. This says that this defines the intensity of analyzer, right? This formula law defines the intensity of analyzer, right? Intensity of light from analyzer, right? Analyzer, right? So this was the last law says that intensity of light coming out from an analyzer is going to be I naught cos square theta. What is the theta? Angle between pass axis. Angle between pass axis of two polaroid. So this is what we have. This is very important formula. Again for exam also. So I can derive why this is a cos square theta over. Look at here, very simple. Amplitude, we are going to talk about amplitude. And when we define the intensity, amplitude is equal to intensity is square of amplitude. Therefore, we got cos square theta. All right, so the theta is given by this. Now, therefore, what we have is if theta is 0 degree, then I is going to be I naught. I is going to be I naught. And if theta is equal to 90 degree, then intensity is reduced to 0. Intensity. Why? Because the analyzer will not allow polarized light to pass through it. Why? Because it is 90 degree, right? And if theta is equal to 45 degree, and it will allow half. That's the one very important part. This is very important part. This is what I have here. Again. Yeah. So this is again example. Unpolarized light is meant to pass through a polarizer, and then this is vertically polarized. And now I just let it pass through a polaroid whose polarization axis is horizontal. So light is going to be zero. And maybe when you come back to school, you will see a polaroid, and you can do external also. Again, this is an example, right? This is polarizer, intensity reduced to half. Now, when this polarization axis is perpendicular to polarizations, so therefore this is reduced to 0. This is an example, right? These two are perpendicular. These two axes are perpendicular to each other. These two axes are perpendicular to each other, right? Light passing through a cross polarizer. That is what we call as a cross polarizer, right? So first polarizer is vertical axis, another one is horizontal axis. So they cross each other. Finally, we get 0, right? So this is the point. Now, now I would like to do one very important topic. That is polarization by scatterings, right? Polarization by scatterings. We are not going to do a detail, right? It's a little tough. Concept a little abstract. So what I'm going to do is a polarization by scattering, right? Let me give you this example. Maybe you just bring up polarites, and you don't see a sun side or a source of light side, and you just focus your polaroid to a sky, whatever. Then you just rotate the polaroid, and intensity will change. There is a variation of intensity of a polaroid. That means what we get is we get a scattered light. So that means the scattered lights are also unpolarized light, but we call the partially polarized lights. So now the here topic is polarization by scattering, right? Now the point is, how are you going to polarize light by what we call as a scattering, right? This is what we are going to learn, right? So every scattered light is not polarized light, all right? This could be unpolarized light also. But some scattered lights are what we call as a polarized light. So this is what we are going to define. This is unpolarized light from a sun. I can define this like this also, right? Approaching, and this is a molecules that scatters particle, right? This is a molecules that scatters particle light. And this scattered light in every possible direction, in entire space. So what we get is this is I, this is observer, this is observer. Now look at here. The first thing is the light is a transverse wave. Transverse wave. So when we talk about transverse waves, propagation is always perpendicular to. Propagation is always perpendicular to perpendicular to oscillation. What oscillation? Electric field oscillation. That you should keep in mind. So I'll just do this in a very simple way, right? So since you are here and lights, this is the unpolarized light, unpolarized in these planes. Let's say YZ plane. This is unpolarized in the YZ planes, YZ plane. And now you see here, and this light, now we have the electric fields can be resolved into two parts. Electric field can be resolved into an x-axis or y-axis, and electric field is resolved in a z-axis. Now, since the light is transverse waves, we won't get the vertical, right, or y-axis electric field along this. Why? Because let's say if I say that it is coming, then this won't become a polarized transverse wave which goes against the definition of transverse wave. So therefore, what we get is we get this part of electric fields. So only this electric field, that is z-axis electric fields, only z-axis electric field would pass through this path. Alright? So this will not allow no y-axis electric field can go along this path. Alright, so therefore, when you observe this, you will see only this electric field. Alright, when you see only this electric field is a polarized light. So when you see along this, look at here, this has to be a 90 degree. So therefore, when you get a scattered polarized lights, if the direction of observer is perpendicular to the direction of incident light, if the direction of observer is perpendicular to the direction of incident light, then the observer will get only polarized light. So this is the point, and this is going to be an unpolarized light, and this is partially polarized light. Why? Because some axis of this y-axis cannot pass go through this. Why? Because this also become this axis. This axis of electric field could not pass through it, could not able to go through this path. Therefore, this is what we call as partially polarized light. Alright, so this is a completely polarized light. This is a partially polarized light. So not entire y-axis of electric field could go through this path. Why? Because this become again a longitudinal wave. That is not possible, right? So this is a completely unpolarized light. So this is what we define as polarization by scattings. This is what we define as polarization by scattings. So I have told you that when you observe sunlight, when you observe a scattered light, and if you rotate this, you see a variation of a light intensity of light. Why? Because scattered lights are normally partial polarized lights. So therefore, when you rotate it, so therefore there is a change of intensities. If it is an unpolarized light, when you rotate a polar light, and there is no change in the intensity. So that shows that scattered lights are. This could be a partially polarized light, could be partially polarized lights. So therefore, the effect that we will see is that when you rotate a polar light and view not toward a source, view toward the sky, and you see the intensity is variations. The variation of intensity is all due to either light is scattered light is a partially polarized light, or scattered light is completely polarized. If it is completely polarized light, then intensity reduces to 0, right? But completely polarized condition is little difficult to get. All right. This is what we define as polarization by scattering. Now we are going to do a last concept of this. This is polarization by reflections. Polarization by reflections. This is what we define as polarization by reflections. Again, this is very important for examination point of view. This is very important for exam. They come in exams. So that means now I have a light. This is unpolarized light. Unpolarized light incident on this is a denser medium and this is a rarer medium. When unpolarized light incident on a interface surface, refraction takes place. This is what we have done. Now what we talk about is that under certain conditions, the condition is that if angle of incidence, let's say if angle of incidence is equal to some particular angle called a Bristol angle. This is what we call as Bristol angle. Bristol angle, right? So look at here. This is a rarer medium and this is a denser medium. And the light passes from a rarer to denser, the bending is towards normals. This is bending is towards normals. And we believe that when the light undergo reflections, when the light passes from a rarer to denser, two things normally take place. One is a reflections, other one is a refractions. Alright? So this is a reflection part, and when we talk about reflections, so therefore angle of incidence must be equal to angle of reflection. That is what we talk about. Angle of incidence must be equal to angle of reflections, right? Now I say that when the angle of incidence is equal to Bristol angles, alright, when the angle of incidence is equal to Bristol angle, then what we get is that the reflected light is perpendicular to reflected light. Reflected light is perpendicular to reflected light. This is the condition, very important condition. So Bristol angle, right? So this is what we call a Bristol angle. So Bristol angle, why? Because when we at only particular angle of incidence, this would happen. All right. So Bristol angle is an angle of incidence at which the reflected light and refracted lights are perpendicular to each other. Why? Because if I change the angle of incidence, the angle of refraction is also going to change, and angle of reflection is also going to change. So that's the reason, right? So the Bristol angle is what we define as it is an angle of incidence at which the reflected light is perpendicular to refracted light. Reflected light is perpendicular. In this case, what we are going to do is, what we are going to get is, look at here. Alright, again the same concept we are going to discuss. Light is a transverse wave. Alright, okay, so alright, since the light is a transverse wave, the oscillation of electric field along our propagation is not possible. Again, oscillation of field along propagation is not possible. Along propagation is not possible. Not possible. Why? Because this is transverse wave. This is simple, simple concept. So, because of which, this light undergo reflection. Since this is a 90 degree, this electric field oscillation is parallel to this. If an electric field oscillation is parallel to a propagation, if this electric field is parallel to propagations, if this electric field oscillation is parallel to the propagation, that means this electric field oscillation is not possible in case of refractions. Electric field oscillation is not possible for reflected light. So that means when we talk about this, unpolarized means how high intensity is oscillating like this, and how high intensity is oscillating in that direction, right? So when the reflected light, this reflected light means or that this particular oscillations. So this oscillation is not found in case of reflected lights. So this kind of oscillation is missing in this reflected light. So what is remaining? So remaining is only this. So this is what we call as polarized light. This is what we call as polarized light. So therefore what I write here is, alright, these oscillations, electric field oscillating in this plane, in this direction is missing in this case. Why? Because this electric field oscillation is parallel to the propagation. So therefore, these oscillations is not possible in case of this reflected light. So therefore, it is what we call as polarized light. So therefore, this is what we call as polarized light. All right. Okay. So this is a polarized light. So now I use Snell's law. Let's say I just put a Snell's law. Snell's law say that sine I divided by sine R is equal to mu. This is done in mu. That is the refractive index. Now I say that I is equal to a Brewster angle. I is equal to Brewster angles. Then again, I'll just tell you this. This is 90 degree. This is 90 degree. All right, and then this is also 90 degree. All right. Now I say that, so this IB, look at here, this angle is going to be, this is 90 degree, so this is 90 degree, this angle is a common angle, so therefore this angle is going to become IB, alright, this is IB, this is IB, angle of incidence is equal to angle of reflections. This becomes IB. So therefore, what is R? So this is 90 degree. Therefore, R is equal to, angle R is equal to 90 minus IB. So angle R is equal to pi by 2 minus IB. Okay. So having this, now I just say R is equal to pi by 2 minus IB. So therefore, sine IB divided by sine minus IB, this is equal to, so this is equal to sine IB divided by cos IB, sine cos is equal to 10 IB is equal to mu. So this is what we call as a Brewster law. This is what we call as a Brewster law. So therefore, the Brewster angle is also defined by refractive index. Or Brewster angle also defined is a characteristic of a medium, right? Two media, right? So Brewster angle is also a characteristic of a two media. Brewster angle is also defined by refractive index. Okay. So this is all about polarization, and application of polarized are there. So polarized are used for used in a different field, like in a glass we use. All right. So in my notes, I've given you a detail about the application of a polarized. Okay. So with this I have done with polarizations, and I have finished wave optic also. So at last, what I would like to tell you is, in this video lessons, I was able to finish two very big chapters, which has 14 marks. So kindly go through those, all right, and kindly go through video lessons and read, see at least 2 times, 3 times, all right, and go through my notes. And I'm sure notes and a video lesson may benefit you, all right. So since this is the last video lessons, so I would like to convey you good wishes, all right, and all the best. Maybe sometime we may see next time also. Okay. So thank you.